today what do we do? So we're going to do some properties of Bessel functions. So we're talking about this Bessel function, which is k equals to 0 to infinity of -1 to the kth power, k factorial n plus k factorial x over 2, 2k plus n. So for this one, there are a few things that I should have said, that but it's not too late to say it because we just finished using these. So the first thing is you can see that this summation starts at n, right? When k is 0, it's x to the nth power. Right? That's the very first term. So what that means is that if n is bigger than 1, Jn of 0 would be 0. So Jn of 0 is equal to 0 if n is bigger than 1. Furthermore, if n is equal to 0, let's think about what happens. If n is equal to 0, what's the very first term? The 0th power, so n equal to 0th power is 1, right? N equal to 0th power is 1, 0 factorial is 1, 0 plus 0 factorial is 1. So everything here becomes 1, and therefore Jn of 0 would be 1. So maybe that's the first property. Second one is because these terms increase by order of 2, if the very first term is odd, then the next term will be odd, and odd, and odd. So the entire thing will be odd, right? So j 2n minus 1 of negative x would be equal to negative j 2n minus 1 of x. Whereas if it starts with an even number, then the entire function will be even. Now there are some asymptotic formulas where formula for Jn, which is Jn of x would be similar to square root of 2 over pi x cosine of x minus 2n minus 1 over 4 pi. Actually, if it's 1/2 power, this is an actual equal sign. X, yeah. Because if you plug in 1/2 here, 2 times 1/2 is 1, 1 minus 1 is 0. So you get cosine x. So you would have said, this formula would say that this would be an asymptotic, So when x is a really large value, then this formula would say that these two are similar, but they actually end up having exactly the same thing. Now this is actually not that hard to prove, this one. All you have to do is you just have to, we haven't done the odd ones, but non-integer ones, but when n is not an integer, this is just changed to gamma of n plus k plus 1, right? And you can further talk about gamma of 1/2 being square root of pi, so on and so on. And using that, you can just write out the series completely. And if you compare that with the series for cosine, you're going to see that they're exactly the same. So it's kind of interesting that they're actually exactly the same. Okay, and then D, for this one, I can't prove it in this class because this relies on some integral representation of Jn, but that integral representation relies on complex analysis. You have to be able to do contour integrals, and that's outside the scope of this class. But this one you can actually check. Okay. All right, and then there's some additional formulas, and aside from part D, it's going to be non-trivial, and we will actually try to do the calculation. Okay. So if I do x to the n times jn x and differentiate this, it's going to be equal to x to the n of j n minus 1x. So let's try to prove that. Okay. Proof. So it's just a straight up calculation from here. You just put that there. So if I have x to the n times j n x, it's going to be equal to summation k goes to 0 through infinity, and then -1 to the kth power, k factorial n plus k factorial, and you have x over 2, 2k plus n, but let's do this. Because I'm multiplying x to the n, this will be 2k plus 2n, right? But those extra n's don't come with over 2, right? So I've inadvertently introduced more division by 2, so I have to cancel the introduced 2 by multiplying by 2 to the nth power. So, yes?
How did you get 2n on an exponent?
Oh, because this is x to the n.
Mm-hmm.
That gets multiplied to x to the 2k plus n.
I see.
Yeah. Or, you know what, maybe that's one way to do it, but let's do it this way. Just break up this thing as x to the 2k plus n over 2 to the 2k plus n. Right? And then we can now rewrite this as 2 to the 2k plus n and x to the 2k plus 2n, because there's an extra x to the n in front, right? Okay. So now let's differentiate this. It's a really straightforward differentiation. Okay? And if you do that, then 2k plus 2n comes in front, right? So you have summation of k goes to 0 to infinity of -1k, 2k plus 2n comes up, and then you have x to the 2k plus 2n minus 1 over 2 to the 2k plus n. Okay. Okay. Now, look at the following. This is, so 2k plus 2n is 2 times k plus n. And that 2 can cancel one of the 2's, reducing this by 1. Whereas n plus k can get rid of this n plus k. So let me ask you a question. If you have n plus k divided by m plus k factorial, what is this equal to? Well, when these two numbers are the same, well, what do you get? That's my question. So for example, if you have 10 over 10 factorial, what is this same as? 1 over? 1 over what? 9 factorial, right? Because this is 1 through 10 multiplied and 10 and 10 cancel, so you get that, right? So in the same reasoning, what would this be? 1 over m plus k minus 1 factorial, right? Right? Okay. So the result is that that integral, that summation is same as summation of k equals to 0 through infinity of negative 1 to the kth power divided by k factorial n plus k minus 1, or k plus n minus 1, let's write it like that, or n minus 1 plus k factorial, and write it as x to the 2k plus 2n minus 1 over 2 to the 2k plus n minus 1. Okay. And now almost everything's done, because now I can factor out the x to the n. And the end result is that you have, once you take the n out, then now they have the same power, so you can rewrite it as x over 2. And you have 2k plus n minus 1. So you can see that this formula is exactly the same as that one, except that n is replaced by n minus 1, right? So what is this much equal to? It's x to the n power j, what? J n minus 1x. Done. Okay. Now, what is D? Okay. E, you have a similar formula. Again, proved in the same way. It's done exactly the same way, except that this time it will be negative x to the negative n, j n plus 1 x. Okay. Now, then after this, we get some additional formulas. And the formulas are, well, let's first figure out what this is saying. This is saying that you have n times x to the n minus 1 j n x plus x to the n j n prime x equals to x to the n j n minus 1 x. Right, I erased this. I shouldn't have erased it, but it says this is same as this. So if you just apply the product rule to this, so the x to the n is differentiated, and then you differentiate the second one, this is what you get. And what we can do further is you can divide everything by x to the n, so that you have n over x, j n x, plus j prime of n x equals to jn minus 1x. So this is from C, and you can divide by x to the n to get that. Now in the same way, if you rewrite this and and this I multiply by x to the nth power, what are you getting? You're getting negative n minus 1, so it's negative n over x jn x plus jn prime of x, and then this would be jn plus 1 x. Is that okay, or should I do the calculation? I skipped some yeah?
Like, what do you do for step F, like on the left-hand side? I understand the right-hand side used, can you remind us what you just did for F, briefly?
Okay. I'll just do the calculation. So let's see, x to the negative n jn x prime, it's x to the negative n prime jn x plus x to the negative n jn prime x, right? Product rule, right? Then this thing comes down, right? So you have negative n x to the negative n jn x plus, sorry, this should be n minus 1 j n x plus x to the negative n jn prime of x. Okay? That's what you're getting, right? On the left side of this equation, E.
But there's a negative n right there.
There's a negative n, right?
Yeah.
Yeah, okay. And then on the right side it says negative x to the negative n jn plus 1. Oh, just a minute. Did I forget a... Oh, sorry. This should be minus, right? Was that why you were asking? Yeah.
Yeah, I think so.
Okay. All right. Yeah. Okay. Yeah. And then what you do is you multiply by x to the n. So you have this equation and you multiply by x to the n, so that these will cancel away. On the other hand, you get x to the n times x to the negative n. That canceling, you still have x to the negative 1 left. Right? So that's why you get this. Okay. Oh, actually, it's good that I actually did the calculation, because I was doing it in my head and then messed up the sign. All right. So now what can you do with this? Well, it's a pretty interesting equation because the terms look pretty similar, right? So you can actually take these and add or subtract and get the other relations. So you can add them, which cancels this but doubles this, right? So double jn prime of x equals to jn minus 1x minus jn plus 1x. Just make sure that's what we get. Right? Okay. And then we can also subtract. If subtracting instead, if you subtract, then this minus this actually doubles this one, whereas it cancels this, right? So you end up with 2n over x jn x equals to jn minus 1x plus jn plus 1x. Now, so I guess this is an interesting thing. If you differentiate something and you get the other, that means the antiderivative of this is this, right? So actually I think this is more interesting than this one, because this would immediately imply that integral of jn minus 1x minus j of n plus 1x dx gives you 2 j n x plus c. Differentiate sine, you get cosine integral cosine sine, right? So that's what you get. So actually we have 4 different things here. So even these can be solved for jn prime, and you get jn prime of x equal to negative n over x jn x plus jn minus 1x. And then this one can be written as jn prime of x is equal to positive n over x jn x minus jn n plus 1x. So you have 4 equations, 1, 2, 3, 4. Okay, and then integral from 0 to 1 of x j n m x squared dx gives you 1/2 j n plus 1 j n. Oh, squared. So that's task 1. Now this is an interesting one as well, because you get for us we had this integral from 0 to a of x jn jnm over a. Well, we had r. So remember this integral? Okay. This was in the denominator when we were calculating, right? And if this is true, we can find the answer for this one as well, because we can just set x as r over a, so that r is equal to ax, and then sorry, this should be dr. dr is equal to a times dx. So this integral now becomes 0 to a. When r is a, x will be 1, right? So x will be 1. R is ax jnm over ar, and then squared. Oh, by the way, jnm is the mth positive 0 of this function. Okay? And this will be x. And then dx, dr would be a dx. So you get a squared out. You have an a here, you have an a here, a squared comes out, and you have 1/2 a squared of Jn plus 1 Jnm squared. And this is actually more preferred than this formula because this one requires numerical integration, but this just requires evaluation of the series. So you can actually rewrite all the formulas that we found out yesterday for A and M and B and M, and we can modify the denominators by this one. Okay. All right. So how do you actually prove it? Well, the thing is, I was going to do this right before coming here, and I was spending most time with the students. I don't know if I can do it at the spot. Let's see. Okay, well, let's try this. Let's try this proof. So remember where this came from. This was from the Bessel equation, x squared y double prime plus 2x y prime, and then plus alpha x squared, actually nx squared. Oh, wait. It should be j n m x squared minus n squared y equals to 0. So let me just make sure. Oh, that's squared, okay. Oh, okay. So there's no 2 here, it's just this. And this should be squared. Okay, so let me try to explain this again. So remember how we had the r double prime r squared plus r prime plus lambda r squared minus m squared y equals to 0. So you remember this was the this was the actual differential equation we got when we were solving the wave equation on the disk, right? And later on, when we solved this, we later found out that lambda is equal to j n m over a squared. And then we found out that for this specific lambda, the eigenfunction was jn m over a times r. So that was the eigenfunction, that was the eigenvalue. Okay. So with that, we're trying to think of a as 1, right? A as 1. Then this denominator will go away. And the interval from 0 to a will now turn into 0 to 1. So we're just trying to simplify things by taking a as 1 in here. And if you set a as 1, the differential equation will now become like this. Okay? But that's just too confusing. Let's just, for a moment, rewrite j and m as alpha. Okay? So what we want to prove is that it's the following. We want to say so we know the following. If this one has a non-trivial solution with some boundary conditions, with y of 1 being 0, because it has to be 0 at the end of the disk, right, rim of the disk, and also y of 0 being finite, then we know that the solution should be a multiple of what? Y should be Jn of alpha x. That's what we know. Okay? So what we want to show is that because we know that, using this equation as something that this satisfies, we know that this function satisfies this, and my aim is to prove the integral from 0 to 1 of x times this y squared, or Jn alpha x squared dx is equal to Jn plus 1 x with 1/2, and this is squared, alpha squared. Okay, so if you just replace Jn by alpha, that's what we're trying to prove. Okay, so let's actually prove it. X squared y double prime. Let's multiply both sides by y prime. So multiply everything by 2y. Okay. So we have 2x squared y prime, and then plus 2xy prime squared plus alpha squared x squared minus n squared y prime equals to 0. Okay. Okay, so let's think about this. If I have x squared y prime squared prime, what would I get? This would be 2x times y prime squared, just by the product rule. First, this gets differentiated, right? And then plus, would be 2 times x squared times y prime times y double prime. Is that right? Right? Just by the chain rule. This comes down and then you have to take the inside out and differentiate, right?
Yes.
Okay. So where do you see this? The first one, first two, right? Okay, and then what about the other one? Oh, did I forget to multiply 2? Okay, I forgot to multiply 2. 2y prime. So I took this differential equation and I multiplied by 2y prime. And I see immediately that this one is this thing squared. Okay, so if I okay, all right. All right, so I'm not so sure, but let's just try it. So if I integrate this, so if I integrate both sides from if I integrate both sides, because this is the derivative of this, I'm going to get x squared y prime squared. Okay. And then this will be equal to, actually you're going to get plus integral of 2 alpha squared x squared minus n squared y prime dx. And you know, we're just going to integrate from 0 to x, if you don't mind. So I should really be saying that I'm integrating t using t, and then after you integrate, then x goes into 2, x goes into t, but I guess that's okay, right? So because x goes into x, this is still true. When 0 goes into 0, it's 0, so you get x squared y prime squared. And then on this side, I'm going to use integrate by parts. Because, again, if you have y squared prime, what do you get? 2y prime, right? So I can integrate this much and differentiate the other. Okay? So let's do that. So the integration by parts is this. Integrate two functions. Then one gets integrated, but then the one that you didn't integrate becomes differentiated. That's the format I like. So this gets integrated, so you have alpha squared x squared minus n squared times y squared. Right? And then minus 0 to, right. We're trying to integrate from 0 to 1. Sorry. So this should really be from 0 to 1. Right. Okay. Sorry, I should be putting 0 to 1 here, and 0 to 1 here. Okay, well, let's see what that gives us. Okay, so now we like what we see, because this is just y squared, but this one you have to differentiate, so that's 2 alpha squared x, and then you have y squared dx equals to 0. The right side is still 0 because you've integrated it from 0 to 1. Okay? Okay, so one thing that you have to know is that we have that the condition for this was that y of 0 is bounded, and then y of 1 is 0, right? So when 1 goes into y squared, you evaluate y at 1, so this becomes 0. Okay. On the other hand, this is just when you plug in 1, it's just y prime of 1 squared. Okay? Because when 1 goes into x, it's just 1, right? When 0 goes into x, that's 0.
Yes.
So you just get y prime of 1 squared. This will be, when you plug in 1, it will be 0. And then when you plug in 0, that's going to be a problem. We have y of 0. Now we know that the functions here are, y is really jn alpha x, where jn of alpha is 0 because the alpha was really j and m, so it was the mth 0 of jn. So yeah, and so there are two cases when n is equal to positive 1 or greater, we know that jn of 0 is 0. So this is going to be 0, okay, when you plug in 0, right? On the other hand, when n is equal to 0, y of 0 is no longer 0, but y of 0 is 1. We said that j0 of 0 is 1, right? When n is 0, right? So unfortunately, when n is 0, this won't be 0. However, if n is 0, this will be 0, and you're plugging 0 into x, so they're both 0. So it's not, this will be 1, but this will be 0, so it will be 0. So this is going to go away regardless of whether n is 1 or 0. Okay? So that's a fine point, but that's what happens. Okay? All right. So that means this is the only thing that we get. And this goes to the other side, and you get this equal to integral from 0 to (0 to 1) of 2 alpha squared x y squared dx. Okay. And this is very close to what we are trying to do. So what was the formula for jn prime of x? What is this same as? Can somebody tell me? This is 1/2 of j n minus 1 x minus j n plus 1 x, right? So that should be, I thought that was going to give us the answer. So if I have oh, no, this is not the one I want. Sorry. It's the other one. Sorry. It's the, of the other things that we had, it was, sorry, it should be, it's n over x, j nx. Which one was the one with plus? It's minus jn plus 1x, right? We had this one as well, right? Is that good? Okay. So if we plug in 1, oh no, not that one. So if I put alpha there, so this would be, you have to be careful because you have alpha. This is going to produce extra alpha squared when you differentiate. So what's going on here? If I differentiate, right? So if I simply use this, okay, all right, yeah. Alpha x, jn, alpha x minus jn plus 1, alpha x, that's what we get. And then y prime of 1 would be jn prime of alpha times 1 which is n over alpha times 1 jn alpha minus jn plus 1 alpha of 1. Okay, so what's jn alpha? Zero, right? It was one of the zeros, right? So that's going to go away. And therefore, what you get is that you get y prime of 1 equals to negative jn plus 1 alpha. So that's what you get. Okay. Now, there is something that I should be saying about the right side, because if you actually write this, we're off by an alpha. So if I actually write this, this is 0 to 1 of 2 alpha squared x j n alpha x squared dx, right? And there's some discrepancy about this one with the formula I wrote down, because there's an alpha there. And the problem is I made a mistake somewhere with the alpha, because this should be absorbed into dx because you have this alpha x. So let's see, or maybe it's the left side. Right. Okay, so what's happening is this. See, y is equal to jn alpha x, right? So there's something that we, so the problem is, if I differentiate both sides, it's not jn alpha x, jn prime alpha x, but it's alpha times jn prime alpha x, right? So because of that, I'm missing on an alpha factor here. Okay, so sorry about that. That's where this. Okay, so then the proof is done, right? So let's try to summarize what we found out, and then if you summarize, you'll see that the solution is there. Okay. So what we have is that we know that y prime of 1 is negative alpha jn plus 1 alpha squared. This is y prime of 1. And on the right side, I have integral from 0 to 1 of 2 alpha squared x times jn alpha x squared dx. And then you square this, minus goes away, and alpha squared can be canceled out, and you divide by 2. What's the final thing you get? Right? So that's what was to be proved, right? So that's the one thing that's relevant to us, where this alpha is really J and M, which is the mth positive 0 of capital J and X. Okay. So that's going to be the last property I want to discuss, because this is directly related to what we were trying to do. Okay. Yeah. So I actually assigned the homework for finding the CNM and DNM of the wave equation using the integral with G, right? And for that one, it would be nice if you can actually use this one as well. Okay. Yeah. So for the homework, please. Instead of using this kind of format, so what was I trying to say? So for homework, please use integral from 0 to a of r jn j and m over a r squared dr to equals 1/2 a squared j and n plus 1 j and m squared. Okay. So instead of writing this, just refer to the calculation we just did and use this. Okay, so I found this nice website by Daniel Russell, which gives you the vibrational modes of circular membrane. And these are the pictures I was talking about. The 0-1 mode vibrates like this, and the 1.1 mode vibrates like this. And it's hard to see from there, but Fn, the fundamental frequency, the lowest frequency, if you say that's 1, then this is 1.6 times the basic. So this is more like, I don't know what that is. That would be like fourth interval or something like that, I think. And then this one is 2.14. That's even 1 octave higher. That's the 2-1 mode. This is 2.30. That's so that's again 1 octave higher and even some more. This is frequency 2.65 times the base frequency. This one, 1-2 mode. And you kind of know what it means. 4-1 mode means it's the J4, the Bessel function of order 4, and 1 is the circular part, the cosine theta one. Yeah, right. So one thing that you have learned from today is the following. I just covered that J0 of 0 is what? What's J0 of 0? So in general, Jn of 0 is what? It's 0, right? Jn of 0 is 0. But what's J0 of 0? 1. That's the only different one, right? So J0 of 0 is 1. So you can see that whenever you have 0 on the first one, that's the Bessel function of order 0. And the middle point goes up and down. Right? But look at 1, 1. That's J1. Do you see the middle one? Does it move? Actually, it looks like moving, but it's actually, the height is always 0. The center point doesn't vibrate at all. Over here, again, the center point doesn't vibrate at all because it's J2. However, if you go to 0-2 mode, do you see that the center point is now going up and down?
Yes.
Because J0 of 0 is 1. This one, again, 3 would be, it will give you 0, 1, 2. The middle point is, like, it looks moving, but at the very center, the height is always 0, okay? Same thing here, but then you get the 0-3 mode, and you see that, again, it's going up and down, right? And actually, when you get to 0 mode, you're just seeing more and more of the Bessel function of order 0. See, when it's at the peak, the cross-section from the middle is really the Bessel function of 0th order. So maybe I should. Bessel function of 0th order. And if I look at the image, this is the graph of Bessel function of 0th order. It starts from 1 and comes down. And as I explained, it gets closer and closer to a cosine function, right? The amplitude goes down like square root of x, 1 over square root of x. And so the 1 over square root of x goes like that, but at further down, it doesn't decay so fast. So the rate of decay is very fast initially, but it's kind of flat. So what happens is that in the 0-1 mode is you're looking only at this much, And 0,2 mode, you're looking at this much vibrating. And 0,3 mode means this much vibrating. Okay, this is the cross section you're seeing at 0,3 mode. See? Right? So if you see that, then now, like, people who don't know differential equations or PDEs will be looking at this picture and just say, oh, it's pretty, but actually now that you've seen the solution of the circular disk, you see more. You actually see the cross sections of these as, oh, this is like part of the Bessel, zeroth order Bessel function from 1 to the very first zero it has. And then you go to the 0,2 mode, you see that, oh, it's like the first two zeros, and then 0,3 mode, you see 3 zeros there, and then that's it. Okay. Now, if you are wondering why the ordering of it's like this, it doesn't seem to have any structure, and it really has to do with the frequency. So this is the lowest frequency vibration, and this is the next high, and as you go down, it has higher and higher frequency. And you see a lot of them is, you see more and more frequency inside the 1 octave higher, and even more in the 2 octaves higher, and then so on and so on. Okay. All right, so that's the one I want to show you. Let's see. Spherical Laplace equation, or PDE. All right, so the spherical Laplace equation, again, it's you have to use spherical coordinate system, right? So I don't know if you remember the spherical coordinate system. It's like you have this picture where the angle from the top is phi, and then you have the usual r that you know of, that's from the polar, and the distance from, so r in the cylindrical coordinates is the distance from the z-axis, whereas rho is the distance from the origin. And then, so this will be z. So this is how I remember it. So it'll be rho times cosine phi gives you a direct projection, so that's going to be z. Whereas rho times sine phi is going to be r. And then because x is r cosine theta, this becomes rho sine phi sine theta. And then y becomes r sine theta. So it's rho sine phi cosine theta. Let's see. Oh, why did I switch this? Cosine theta, and sine theta. So with this one as the last one, this is what we call the spherical coordinate system. And to give you an idea, it's like opening a book, right? So let's say you have a point in space that you want to express using the spherical coordinate system. You open the book until this page hits that point. This page covers that point. This angle that you open is called theta, right? And from the North Pole, you draw down a vector until you hit that point. This angle is called phi. And the distance from that point to the origin is called rho. Okay, so using the three numbers, rho, theta, phi, we have the description of any point in space. So that's called spherical coordinate system. Now, because we have a transformation, then of course, we started the very first class I gave was about changing the derivatives, right? Partial derivatives into another coordinate system. And of course, you can do it, except that it's really painful. So I myself made a YouTube video on writing the Laplacian, which is partial x squared, partial y squared, plus partial z squared. I myself made this change of this into the spherical coordinate system, and it took me 40 minutes on the video, which usually means I'm trying to be very efficient in the video, and it still took me 40 minutes. So if I actually did this calculation here, it's going to be more than 1 hour. So it's a very complicated calculation. So I'll just have to refer you to the video if you want. You're interested to see how it's done. But it's see, you've already tried the polar coordinate one because it was part of the homework, right? It's just the same type of idea, just more boring calculation, but with 10 times more work. It just gets, it's a lot harder, so you don't really want to do it. Okay. So what is this? Well, this is 1 over rho squared sine phi, and then this is partial of r rho squared sine phi, not rho, partial of rho, plus partial of phi sine phi, partial phi, and then plus partial theta, 1 over sine phi, partial theta. It's this one. Yeah, I actually had to spend time memorizing this, so it's not at all obvious to me. And I tried to look up some other sources where they explain why this would be, but I still don't know. It's kind of elusive. All right, so now before I actually solve the Laplace equation in spherical coordinates, I'm solving 3D Laplacian, but with spherical coordinates. I'm going to switch things around. First of all, I'm going to change the inevitable. Instead of writing rho, I'm going to use r. So my rho will be really r. Okay? So r is going to be the distance from here to there. Okay? Yeah. And we're not even going to talk about this r. That was from the cylindrical. Now, why do you do that? Well, it's inevitable because, you know, in Greek letters, do you know what the capital of rho is? It's P. If this is capital rho, P is capital rho. So when I do, so first of all, rho is really confusing to begin with, but instead of saying r of r, I have to do this. It's like ridiculous. So I don't want to do that. So I've never seen anybody solving Laplace equation with the rho, so I'm going to use r instead. And then I'll have to do another change, just because many people do it this way. So instead of phi, I'm going to use theta instead of, so the phi and theta will be switched. And this is, we have to blame the physicists because, I mean, if you look at the math, obviously, phi should be from the North Pole and theta should be the angle that you open the page, just because it goes well with the cylindrical, right? But somehow physicists didn't like that, and they were using phi for what mathematicians use for theta, and theta for what mathematicians use as phi. And guess what engineers do? Engineers took the physicists' ideas, and then most of the work here is done with these two switched. Right? So if you look up any solutions on YouTube videos or online PDF files, it's more likely that you're going to see these two switched. So I'm just going to follow them. Right? Okay. So let's write down the spherical Laplace equation with that. But we have to first decipher what this is. Okay, so what is that? That's so in terms of r squared sine theta, differentiation by r squared sine theta, differentiation by r plus differentiation by theta, sine theta, differentiation by theta, plus differentiation by phi, 1 over sine theta, differentiation by phi. Alright, so let's write down. This is the most complex form that I like to memorize, I found to be, because, you know, do you know where this comes from? This is the volume form, right? In spherical coordinates, dv equals to rho squared sine phi d rho d theta d phi. Have you seen this? Remember that? So that's the volume form. So that's how I remember it. Right. Okay. All right. So what this is saying is, you know, before that, let me try to explain what this means. So I think so many people are going to be confused when they see this. You see, an operator like this only has meaning if you apply it to some u. Okay? And when you apply it to this u, it's really a composition of operators. So the way you're thinking of it is you have this, this, and this. Okay? So when you're differentiating this, when this hits this, you have to use the product rule. Okay? So when you use the product rule, when this hits this, you get r squared differentiated by r gives you 2r sine theta, right?
Yes.
And then when this hits this, what happens? R squared sine theta, and then you get this squared u. So it's u double prime. Okay.
So we can simply square dr?
Yeah, so this means you're differentiating u twice in r.
I see.
Okay. So because of that, this should be written as 1 over r squared sine theta as 2r sine theta derivative of r plus r squared sine theta, 2 derivatives in r. And that happens as well. When this hits this, that's cosine of theta, differentiation of theta. But then this is actually product rule. So then this could hit this one. So that's going to give you sine theta, differentiation twice. And then this thing is independent of phi. So when this hits this, what happens? It's 0, okay? So for this one, when you apply the product rule, nothing happens. When this hits this, it's 0, and this just gets over here. So this is 1 over sine theta derivative with respect to phi squared. Okay. And then finally you divide this out, and I guess the preferred one is the problem is I like to do my product rule backwards than most textbooks. So if I follow the textbook way where I put this first and then this, then this would come first, right? So this divided by this is 1, so this is squared. And this divided by this gives you just 2 over r. And then this divided by this, sine theta will cancel and you get 1 over r squared derivative of theta squared. And then when you divide this by this, you get 1 over, actually cosine theta divided by r squared sine theta derivative. And then finally, when you divide this by this, you get 1 over r squared sine theta squared. Okay. And remember, phi is this one, so phi goes between negative pi to pi. And then what's the range of theta? All right, so now you're ready to actually write down the differential equation. Okay. So let's say you have, so what is Laplace differential equation? It's the Laplacian of u equals to 0. And in our case, it'll be urr plus 2 over r ur plus 1 over r squared u theta theta plus cosine theta over r squared sine theta u theta plus 1 over r squared sine theta sine squared theta of u phi phi equal to 0. And then there are some additional boundary conditions. So we're going to say that the boundary condition is u a phi theta equals to some function of phi theta. So that what we're seeing is that you have this sphere of radius a, right? And then well, actually, there are two kinds of Laplace equations. If you have a ball, and let's say the ball is not a metal, it's not conductive, so that if it's conductive, then immediately you have the same voltage around it, right? But if it's not conductive, you might have different charged places. So maybe some places might have higher voltage and the electrons can't move freely, and then you might have some distribution of f phi theta. Okay, and in that case, you can talk about the electric field, voltage inside the sphere. Okay, so you have some prescribed voltage outside. Then inside the sphere, at each point, you have the electric potential at each point, and you might ask, what is the electric potential at those points, right? Or if you have a charged surface, also it makes sense to ask voltage outside, right? And depending on the viewpoint, you may have, you'll see that later. I'm going to be coming back to this point, but depending on the situation, some solutions won't be physical, and some would be physical. Okay, so that's the comment I want to make. And actually, you can solve both. You can say, you can solve one Laplace equation inside the sphere, and you can find the solution of another Laplace equation outside the sphere. And the only thing they have to agree on is that their values, the electric potential has to agree on the surface of the sphere. Okay. So you may remember from the physics 2, the physics class you almost failed, right? Yeah, that was the hardest one, right? Yeah, I think that's, including me, it was the hardest one. But if you look at the electric potential, what happens is that the graph of the potential is that until you get to the surface, the electric potential just increases like that, right? And then after that, it decreases like 1 over r. You remember this picture, right? Yeah. So if we solve this for a constant boundary condition, that's exactly what we're going to get. We're going to get that the solution is like that, and then yeah. But that's actually, of course, you're going to see that solution, but it's just not worth it. We're doing so much work here just to get that. It's not a good thing to do. So I'm going to point it out, but it's not what we want. Okay. All right. So let's try to solve this. Step 1. What's our step 1? We've done this so many times now. Everyone knows, right? How do you do it? U R phi theta equal to R phi of phi theta of theta. Okay, and then you plug this into this gigantic equation, and you get R double prime of R phi of phi theta of theta. You know what? It's just so much writing that let me just not write down the variable for now. Okay, so I'll just write R double prime phi theta. Okay, is that okay? Mm-hmm. And then we will write 2 over R prime phi theta plus 1 over R squared R phi theta double prime plus cosine theta over R squared sine theta R phi theta prime plus 1 over R squared sine theta, and then R phi double prime theta equals to 0. All right, so that's what we got. And now what's the next step?
So we do the separation of variables?
Yeah, we're doing separation of variables. Okay. So we divide everything by
so
R phi theta, right?
Yes.
So we divide that. Except that if I really want the separation of variables, I think we should also multiply by R squared sine theta, so that you have one part where you only have a function of phi and the other one as something that doesn't have a function of phi. Okay.
Shouldn't that be sine squared theta?
Oh, thank you. Oh, thank you. Yeah. Oh, so then we have to multiply by R squared sine squared theta. Okay. So after this, and then multiply by R squared sine squared of theta. Let's see what we get. We get R double prime over R, and then R squared sine squared of theta, plus 2 over R prime over R, times R squared. So this is actually 2R sine theta, and then plus theta double prime over theta, and then sine squared of theta. And then it would be cosine theta sine theta, theta prime over theta. And then we can finally move this to the other side and make that as phi double prime over phi. Okay, so what now? We can now look at this and immediately say that the left side only depends on r and theta. I don't see any phi. Whereas on the right side, I don't see any r or theta, I only see phi. So I've separated the variables, which means that the only way these two could be equal is if it's equal to some number. Okay? And the number that I want is, I just want it to be lambda. Okay? So let's put it as lambda. So that this becomes phi double prime plus phi double prime equals to negative lambda phi, but if you move it to the left side, it's lambda phi equals to 0 with the periodic boundary conditions, right? So phi is from negative pi to pi, so this is true, and then also phi prime of negative pi is phi prime of negative pi. So with these conditions, what do we know about phi? What could phi be? Oh, I thought we did this so many times.
Well, lambda would be n squared.
Yeah, and then lambda is n squared, and
A cosine n theta.
right. So you get a cosine n theta. Actually, we shouldn't say theta.
Oh, it's
Now it's phi. Okay, b sine n phi. Okay, so that's what we get, and lambda is really equals to n squared. Actually, there's a 0 also works as well. So this is n equals to 0 or above. Okay. Okay, so we have that, and then let's see. So here's what's happening here. Did I forget something? Oh, this should be sine squared, right? Yeah, this should be sine squared. Okay. Okay, so then, now with this n squared, I can move these to the other side and divide it by sine squared, right? And the result is the following. Yes?
Can you remind us how we figure out what phi is equal to?
What phi is equal to?
Yeah, like part of the
This one. So this is Sturm-Liouville. Yeah.
okay.
It's a Sturm-Liouville problem. It's not the usual one, but we've done this calculation where you impose these periodic conditions, and we find out that for each eigenvalues there are actually two linearly independent solutions, and they can be these from n starting from 0. All right, so what we do is now we move everything to the other side, and this time we divide by sine squared, because then we separate this out, and there will be a constant, right? So we have r double prime over r squared plus 2r r prime over r equals to negative theta double prime over theta minus cosine theta over sine theta, theta prime over theta. Because we're dividing by sine squared. And this one will also be divided by sine squared, so it's n squared over sine squared. Sine squared of theta. Okay, and again we apply the separation of variables. Left side only depends on r, the right side only depends on theta, therefore they must equal to a constant. We set it equal to a constant. And now here's another fine point. Now we can just set this equal to mu this time. But don't write this because I have to. We're going to actually write something else. Now, if that's equal to mu, here's what we get. We get r double prime times r squared plus 2r r prime, and then minus mu times r equal to 0. And this is what's called the Cauchy-Euler equation. And so earlier on, we had a similar equation when we were doing Laplacian on a disk. And I just said it's Euler equation. I looked at the literature. People say Cauchy-Euler because Euler equation actually has another. Euler has another important differential equation that's for fluids, incompressible fluids, or some inviscid fluids. So just to distinguish that, I think more people try to say Cauchy-Euler. And Cauchy-Euler simply means this. If you subtract the number of derivatives minus the number of r, then you get 0. So here's 2 derivatives minus 2, you get 0. 1 derivative minus 1, you get 0. No derivative, no r, so 0 again. Okay? In such a case, and this is something that we observed in the, what was it? We observed this in the Laplacian equation in the disk, which was that the solutions look like r to some power. Okay? So you just plug this in and solve. The problem is if you plug it in here, then you get k times k minus 1 plus k times 2r. No, see. Sorry. If you plug it in here, it's k times k minus 1 r to the k minus 2 times r squared plus 2r times k times r to the k minus 1 minus mu times r to the k equals to 0. So if you divide by r to the k, those go away. This one go away, this one goes away, and you get k squared minus k plus 2k minus mu equals to 0, whose solution you can find, right? But to solve this, you end up using the quadratic formula, and it's not pleasant, right? It's k squared plus k minus mu equals to 0, and you get k equals to negative 1 plus minus square root of 1 plus 4 mu over 2, something like this. It's really hard, right? But, you know, at the end of the day, this is just some constant, right? And it'll be easier to pick something which makes this lot simpler, right? So for that reason, what we're going to do is we're going to rewrite this one as L times L plus 1. Okay? And if you do that, here's what you get. You get this is L times L plus 1, R equal to 0. And again, all I did was just rename this one to something new. So if I plug in R of R as R to the K and see what we get, and the result is that k minus 1 plus 2k minus L minus 1, L plus 1. And this one magically can be factored because k squared plus k minus L squared minus L is what you get. And you can take these two and just do difference of squares. So it's k plus L, k minus L. And then there's another k minus L. And these two are the same, so if you factor that out, you get k plus L plus 1 and k minus L. So magically, with this, I mean, any constant can be written as this for some L, right? And with this L, we have a solution which says k, so for this to equal to 0, k must equal to L or negative L minus 1. Okay. Which tells us that you have k, you have R of R equals to R to the Lth power and R to the negative L minus 1. All right, so now it's a good, now we can talk about this earlier comment about the sphere. Okay? Now, this means in general, I have something times R to the L plus something times R to the negative L minus 1. Which one's physical if I want to solve inside the sphere? So we assume that L is some positive number, okay? If L is some positive number, which one is physical, which one is not, inside the sphere?
What do you mean if it's not physical?
I mean, in real life, everything is bounded, right? You have some bounded value. So if you have something that's going to infinity, that's not good.
I see.
Yeah. So which one is not physical? What is this? This is 1 over R to the L plus 1, right?
Yes.
So when R is a small value, what happens to this? Becomes infinity, right? So you're going into the sphere near 0. What's happening to the electric potential? It's going to infinity. Does that sound reasonable? No. No. So if you're solving inside the sphere, it's this one that's physical and this is not. Now, what if you're solving outside the sphere? Which one is physical? What? This one's physical, right? And this is not physical. Because what's like this? This is, you're going further and further away from this charged one and you're saying that the voltage is increasing. You have higher electric potential as you go away. That doesn't make sense, right? So it must be that this should be, this is the physical one inside the sphere and this is the physical one outside the sphere, okay? So we have to choose both, one or the other. Now, an interesting thing is, if you have two charged spheres, so imagine that you have a sphere inside a sphere and they're both somehow charged, and you want to solve this, then both are physical. And you have to somehow figure out both, right? So that's even tougher, right? Okay. All right, so we will have to continue this next week. I'll talk about what happens with the data. Okay.